Hey YouTube, what's up? Dr. T here from St. Petersburg, Florida. So, before I get to the subject on hand, a quick promo. Here we have my Twitter account where all of my YouTube posts are presented. If you are on Twitter, you can also follow me from here, from this address, Anthony Hadfield at, it's HADFIEL7 on Twitter. Just to let you know there's an alternative pathway. A few days ago, I introduced a new topic to my channel called Specials. With SpaceX so much in the news of late, there followed posts on the James Webb Telescope, the Higgs boson and beyond, and dark matter. For the moment, let's continue our adventures in cosmology. The Nobel Prize for Physics in 2017 was awarded to the discovery of gravitational waves. Like many of you, I had never heard of this phenomenon. So in this post, let's find out just what gravitational waves are and what is all the fuss about.
The Royal Swedish Academy of Sciences has decided to award the 2017 Nobel Prize in Physics with one half to Rainer Weiss and the other half jointly to Barry C. Barish and Kip S. Thorne, all of them members of the LIGO-Virgo collaboration. And the Academy citation runs for decisive contributions to the LIGO detector and the observation of gravitational waves. And here, as you see, we have our new Nobel laureates with us on the screen above me. A little bit of information about them. Rainer Weiss was born in 1932 in Berlin, in Germany. He received his PhD at the Massachusetts Institute of Technology in the United States, and he is still affiliated with the MIT as professor of physics. Dr. Weiss is, since many years, a US citizen. Barry Barish was born in 1936 in Nebraska, in the United States. He's a professor of physics at Caltech, the California Institute of Technology. And finally, Kip Thorne was born in 1940 in Utah, in the US, and he's currently professor of theoretical physics at Caltech. And as I mentioned, all three Nobel laureates are members of the LIGO-Virgo collaboration, a large team of more than 1,000 scientists who built and ran the detector that was used to discover gravitational waves. And with that, I'll give the word to the chairman of the Nobel Committee, Nils Mortensson, who will give us a brief summary of the research field and the discovery that has been awarded today. Nils.
On the 14th of September 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, succeeded for the first time to directly observe gravitational waves. These waves were predicted by Einstein 100 years ago, but until now they have escaped direct detection. This is a truly remarkable achievement, which crowns almost 50 years of experimental efforts by hundreds of scientists and engineers. And today, the LIGO collaboration includes 1,000 members from 90 institutions in 5 continents who have directly or indirectly contributed to this breakthrough. This year's Nobel laureates represent in an excellent way the diverse competencies needed for LIGO's success. Rainer Weiss led the foundation for the detector design. He analyzed what performances had to be reached for the critical parts of the instrument and what sources of background noise had to be mastered. And Kip Thorne, also a co-founder of LIGO, made predictions about what signals were expected from different astrophysical events of critical importance for the design. Barry Barish is a scientific leader who scaled the project up in a stepwise fashion up to the advanced LIGO, thereby reaching the sensitivity which will in the end allow the successful detection. Without them, the discovery would not have happened. We now witness the dawn of a new field, gravitational wave astronomy. This will teach us about the most violent processes in the universe, and it will lead to new insights into the nature of extreme gravity.
Okay, I'm Rainer Weiss, W-E-I-S-S. I'm an emeritus professor of physics at MIT.
What was your initial reaction when you first saw the signal and you felt like
Well, I was on vacation when I saw it. I was up in Maine. And everybody has their own story about this, I'm sure. But I was in Maine, and my family was with me. I mean, my wife and my son and his wife. My daughter was not there. She was in Singapore. And I woke up, I went to the computer as I do every morning, and I look at the log. You know, we have logs that come from the sites. I do that every morning. And I noticed something funny. They had canceled something that was going to, we had always had. These are days when you fix the apparatus. They canceled it. And I said, that's strange. What the hell happened that made them cancel that? So then all of a sudden I got an email from David Shoemaker, who you're going to be talking to. He says, hey, there's something interesting that happened. So I call MIT and I find out what it was. That was and then I said, holy mackerel. And of course, I gave it all away. Everybody knew it who was around me. I mean, you can't keep that a secret from your wife. She's sitting right there, you know, and my son says, what the hell happened? You know, and suddenly, of course, everybody had to be sworn to secrecy, but okay. And anyway, and then we followed it from there. So that's how I found out about it. But other people, more dramatically, were at the sites, and nobody right away believed it. Everybody thought it was a fluke. It was too good. And it took us a while to get to the point where all of us, and that's why we've written this paper, believe it.
LIGO stands for the Laser Interferometer Gravitational Wave Observatory.
LIGO is really two observatories that work in unison and tandem. The LIGO interferometer has arms that are about 2.5 miles long, 4 kilometers. We have a laser. The laser produces the purest light you can possibly make. It produces light that's so coherent that it's capable of detecting gravitational waves.
We have these very massive mirrors. They weigh 40 kilograms, which is about 88 pounds. They're about this thick, and they're just the purest material you can imagine.
Gravitational waves were predicted by Einstein about 100 years ago, and they are dynamical perturbations in the fabric of space-time. Ripples in space-time, if you will.
A ripple in the fabric of space and time, the same way as a ripple on a pond is a ripple in the shape of the surface of the water.
Nobody really believed that you could ever detect them because the size of the effect is so small. 1/1000th the diameter of a proton.
Even Einstein himself never thought a detection would be possible.
I tried to do this back in the 1960s when I was a student. We couldn't make any progress. We didn't have the technology.
The idea was extremely simple, and it turns out to be the basis of LIGO. What the gravitational wave does is it stretches space this way and compresses space that way. So you exploit that property. Put one object here and another object over there, and let the gravitational wave go through that system, and it'll change the space between these by contracting that one and extending that one. And I came to the conclusion that if you made this long enough, if you didn't make it a little pipsqueak thing like this, but you made it sort of kilometer scale, you could probably get these extremely precise measurements.
Two black holes merging together, literally nearly the speed of light, to produce a bigger black hole. How cool is that?
I said, holy mackerel.
This is the beginning of a whole new way of studying the universe.
It's monumental. It's like Galileo using the telescope for the first time.
Every time we have pointed a new instrument into the sky, nature has revealed secrets to us that we haven't known before. And so I feel very confident that this is just the beginning of such an era for gravitational wave observations as well.
Who knows what we'll see?
I would love to see Einstein's face if he could read this article that we just put out. I mean, he would have been as dumbfounded as we are, because it's a wonderful proof that all of this incredible stuff, the strong field gravity, is in his equations. Just imagine that. To me, that's a miracle that that happened. Man's thinking, and also all the elegance, not only in the theory, but the elegance in the experiment. I mean, that is a human endeavor that I think everybody in the world should be proud of.
On September 14, 2015, scientists in the LIGO scientific collaboration directly observed for the first time the existence of gravitational waves. And not only that, they were also able to determine that the source of these waves is the product of a collision between two massive black holes, 1.3 billion light-years away, a remarkably extreme event that, until now, had not been observed. Now, for the second time, scientists have detected gravitational waves, this time emanating from slightly farther out in the universe, at 1.4 billion light-years away. On December 26, 2015, LIGO detectors picked up a faint signal, which scientists have now determined to be gravitational waves produced by the collision of a second pair of black holes. The black holes orbited each other at half the speed of light before merging into a collision that produced as much energy as our sun, in the form of gravitational waves. These black holes were less massive than the first pair, and produced a much subtler signal that LIGO scientists were nonetheless able to detect using advanced data analysis techniques. The scientists converted the gravitational wave signal into a sound and compared the resulting audio with that of the first gravitational wave signal. That signal produced a clear and sharp chirp that scientists could clearly see in the data. The second signal was subtler, producing a more muted and slightly longer chirp. This new detection once again confirms Einstein's theory of general relativity and also proves LIGO's potential for detecting extremely faint gravitational waves traveling from the farthest reaches of space.
For the first time, astronomers have detected a single cosmic cataclysm in both gravitational waves, ripples in space-time itself, and electromagnetic waves, what we typically call light. This hugely collaborative effort includes the LIGO and Virgo gravitational wave observatories, along with a multitude of telescopes in space and on Earth that, together, collectively monitor the full spectrum of light. The spectacular event was produced by the collision and merger of two neutron stars. These objects are the burnt-out remains of giant stars that have exploded as supernovae. They leave behind cores of exotic matter composed primarily of neutrons crushed together under the intense pull of gravity. More mass than our Sun is compressed into a sphere that is about the size of a city. Astronomers have long known that neutron stars are found in pairs, orbiting one another. The theory of relativity predicts that the motions of these incredibly massive objects should generate gravitational waves. These waves would drain energy from the orbiting bodies, causing them to slowly spiral together and eventually collide with each other in a spectacular explosion. On August 17, 2017, a gravitational wave, CHIRP, was recorded by the National Science Foundation-funded LIGO observatories, and less than 2 seconds later, a short burst of gamma rays, a high-energy form of light, was detected by NASA's Fermi telescope. Researchers quickly realized these two fundamentally different types of waves could have come from a single neutron star merger. If so, it was critical to identify exactly where this had taken place in the sky and if the explosion could be seen by other telescopes. The Fermi data indicated the burst came somewhere from a patch of sky covering about 1,200 square degrees, an area equivalent to 6,000 full moons. Adding information from an independent gamma ray detection from the integral satellite, the search area was further reduced. The LIGO observatories placed the source somewhere in long, narrow strips of the sky, one of which overlapped with the target patch. The Virgo Gravitational Wave Observatory in Italy, working in conjunction with LIGO, should easily have been able to detect a signal of this strength, but saw almost nothing. This was an important piece of the puzzle, since any gravitational wave observatory has a small number of blind spots where it cannot detect an incoming signal. Restricting the source location to Virgo's blind spots further narrowed the search area down to approximately 28 square degrees, or 140 full moons. Around 50 candidate galaxies were identified in this area for follow-up observations using optical telescopes. Less than 11 hours after the first detections, astronomers using the Carnegie Swope telescope identified a previously unseen blip of light in the outer reaches of the galaxy named NGC 4993. Several independent confirmations were reported from other telescopes over the next hour. The first ever optical counterpart to a gravitational wave event had been found. Knowing exactly where to look, astronomers began an unprecedented campaign of follow-up observations using more than 70 telescopes around the world and in space. During the course of the next 2 weeks, a neutron-star merger was detected across the entire electromagnetic spectrum. The gravitational wave data have, for the first time, provided a direct measurement of the masses and orbits of a neutron-star pair before their collision and merger. The data also enabled ongoing follow-up observations across the electromagnetic spectrum, characterizing the explosion and revealing how such unimaginable events have played a formative role in shaping the world around us. These results, for the first time, confirm that neutron-star mergers create precious elements like gold and platinum, as well as a host of other heavy elements all across the periodic table. Explosions like these, through our cosmic history, have seeded the universe with the materials that later would form new stars, new planets, and beings like ourselves who look up and wonder.
LIGO's hits just keep on coming. After its first detection of merging black holes, swiftly followed by finding 3 more, and then a Nobel Prize, the pair of gravitational wave detectors has made yet another huge discovery. On August 17, 2017, the observatory detected gravitational waves from 2 neutron stars spiraling together and merging. Just 2 seconds later, a so-called gamma-ray burst was detected by NASA's orbiting Fermi Gamma-Ray Space Telescope and its Swift Space Telescope. 12 hours after the wave was detected, a team from Las Campanas Observatory in Chile reported a new glowing optical source in galaxy NGC 4993 that was consistent with these findings. And with the advanced tip from LIGO, both radio and X-ray emissions were found a few days later, coming from the same neighborhood. Not only is this the first time LIGO has detected gravitational waves from a neutron-star collision, it's also the first time that electromagnetic observations from conventional telescopes accompany the gravitational waves. At wavelengths ranging from ultra-short gamma rays to very long radio waves, the event was seen by observatories around the world. Because we now have visual information to go along with the gravitational waves, new discoveries are being made about the nature of neutron stars. The light coming from the collision showed spectral traces of lanthanides, a group of heavier elements towards the bottom of the periodic table. This strongly suggests that merging neutron stars have been responsible for the creation of heavy elements such as gold and platinum, a long-held theory. Not only that, but the shape of the gamma-ray burst was unusually weak. Gamma-ray bursts are usually so strong that researchers assume that the gamma rays emerge from 2 back-to-back jets that shoot out of an explosion like narrow spotlights. The weaker gamma-ray burst suggests it was produced when broader jets slammed into a cocoon of matter surrounding the merged neutron stars. While this finding is home to a lot of firsts, it won't be the last. Researchers are positive that with the large amount of gamma-ray events out there and the increase in both gravitational and electromagnetic detector sensitivity, we'll be seeing a lot more of these combination events in the future.
So there you have it. A little bit of research, get a few videos, put them together, and get a complete picture from start to finish of an interesting subject I knew virtually nothing about. Now I know something about. And if you find this interesting, subscribe and you'll get more stuff coming your way in the near future.